All right, hello internet. So, welcome back. It's been a little while since we've seen each other and had a conversation. So I wanted to give you somewhat of an update. We're here to do a few things. So first things first is I've decided to divert my attention for a little while, at least temporarily, towards the Web3 space. So a lot of blockchain stuff, specifically blockchain security and security around smart contracts. At least that's the start of this journey. And I plan on kind of dipping in and out of blockchain security, application security, DevOps security, all that stuff. But I wanted to kind of show you some of the paths that I decided to take and also point out a blog post that I recently put up. So if you go to my website, which is amazing if you do, is this blog post here. It's basically kind of called The Journey Back, and if I go back here, you can see the title. It's basically stating this is in, out, then back into crypto. So back in 2016, I was kind of obsessive with this topic, and I spent quite a lot of time inside of it, thinking about it, talking about it, training people on it. And here's a super duper old video from 2016 of me talking to one of my friends and explaining it to them. Below this is a few years later in 2018 or 2019 when I was doing a few conference talks with one of my buddies. And basically from then I kind of went on a hiatus away from blockchain and actually dove more into cybersecurity. And I've now decided to kind of revisit this topic with a new lens, specifically the lens of focusing at the intersection between my interest in security and my interest in blockchain, which is aka blockchain security. So the first path I'm going to take here is this bootcamp called Secereum. So Secereum is delightfully and amazingly created so many free and open resources to kind of reduce the learning curve and reduce the ability to curate interesting information together to kind of kickstart somebody on the kind of auditing security blockchain ecosystem. So this is the Substack for Secereum. It's kind of a synopsis and an about of what they're trying to do. And inside of their Substack, they have a series of posts that they've posted. And really, there's these, I think, 10 or so posts that take you through each of the kind of topic areas that you would need to understand to have a better grasp of how to audit a security contract for blockchain. So I've completed Ethereum 101 and Solidity 101. I'm working on 201 for Solidity. In this video, I'm going to explain Ethereum 101, and then next video, I'll do Solidity 101 and potentially 201 mashed together. So with that being said, one of the resources I wanted to point out here is this amazing, basically GitHub repo that has gone through the process of completing many of those 101 courses for security related topics in relation to auditing contracts. And they basically, you can see there's a series of videos as well. So there's these blog posts, right? And in addition to the blog posts, they have a YouTube channel for Secereum, and they have all the playlists, and every single playlist is associated to each one of those blog posts or Substack submissions, I guess I don't know what you call them, inside of these videos. So you can watch videos, read the content, and do all that stuff simultaneously. And in addition to all that stuff, there's quizzes. So you do all this content, you read some of the extra assignments if you'd like to, and then you take the quiz. And after you've taken the quiz, you move to the next piece, and you kind of work your way through it. And in addition to all this stuff, one last thing is actually Discord. So they have a pretty amazing and active Discord that basically has a series of people either that are already in the space and pretty prominent, or there's people like yourself trying to get upskilled on the topic. And I think one of the best parts is they have this entire section of mentors, so you can actually speak with people that are working in the space and that are somewhat well known. For instance, this individual named Sam, he's pretty prominent in the space, and you can see he's active currently. So it's pretty amazing to know that this ecosystem is so welcoming and opening to a lot of traditional security folks, and also people have gone on hiatuses for a little while that want to revisit it. So that's all that. And with all that being said, let's get to the first topic for the first video, which is Ethereum 101. So with all these videos, specifically, I've created a series of notes for myself, pulling out images, graphics, code snippets, things like that, that help me intuit the idea and the abstract concept better than just text. Because you can see throughout a lot of these posts, it's just straight up text. It's text and links. The links are nice because it kind of links out to additional resources that'll give you more information. Like this one, for instance, is showing you kind of statistics around the mainnet. There's also a lot of links out to the Mastering Ethereum playbook and all that stuff. But for me, I'm a big fan of images, pictures, code snippets, really for me to understand concepts, especially abstract concepts, in a more intuitive and kind of longer lasting method. So that was kind of my approach there. And in addition to some of these, the videos will be short and long depending on the topic. So for instance, the Ethereum 101 post is a lot of stuff that I've known previously from my kind of previous experience in this space. So I didn't necessarily have to kind of really dive deep in every single topic because I've done that historically. Solidity 101 is different. There was a lot of stuff in there I didn't know because I didn't spend time much in Solidity when I was kind of originally in the space in 2016. So that video is going to be a lot longer because there's a lot of more stuff that I had no idea about. But with all that being said, there's a lot of preface here. I wanted to dive into the notes. And I want to share some of the highlights here of areas that I've known about or maybe I've not known about, or a new take on something that kind of resonated with me. So let's start with some of the notes I've pulled from Ethereum 101. So the first one here is state transitions. The concept of state is something I've heard of and I've kind of understood, but I didn't necessarily know what it meant in the context of Ethereum. So I went to Wikipedia, found some information, got some guides and stuff, and I wanted to kind of walk you through what I found out. State transitions, one of the probably more simplistic but easy to understand explanations of this is thinking about a turnstile as you go into a gate or whatever that is. And a turnstile has you can think two separate states. So one state here you can see is locked and one state here is unlocked. So each of these states take inputs. So one input could be a coin and one input could be a push. So if you want to go from lock to unlock, you first need to put a coin in the turnstile. Next, as you push that turnstile, you're actually going to relock it after you've unlocked it for yourself. So with a state and a state transition, there's a few elements that matter. Those are the inputs, and then they're the state. So those are the two things that matter right there. So the inputs and the state. In the context of Ethereum, what does that actually mean? So here's a little kind of definition that I pulled that I found somewhat understandable and interesting. But if I actually take a step back here and take you to a book that I'm reading currently as well, which is called Mastering Ethereum. So we'll do Mastering Ethereum. And the beautiful thing about this book is it's freely accessible via GitHub. So you can read all this stuff either on your computer, on your phone, wherever you want. And inside of here, there's basically a series of links that goes to all the chapters. And in this first chapter, you'll see there's a specific section that talks about an interesting concept when thinking about Ethereum. And that's specifically here, this sentence. And you can see it states a singleton state. So the way that I've understood this and the way that it kind of resonates is that Ethereum, the ecosystem in itself, is a globally maintained, sustained, and accessible singleton state machine. And that's kind of what made Ethereum what it is today, is the fact that they have an Ethereum virtual machine and it's Turing complete. All these things are making it more practical and more malleable for developers in comparison to Bitcoin. So that singleton state machine really resonated, and within that singleton state machine, there's a series of states that can change within the overall ecosystem. So if I take you back over to this sheet here, we can kind of draw out some stuff that might make sense. Maybe it won't, maybe it will. I don't know, we'll find out. So imagine this massive blob is Ethereum. And inside of Ethereum, there's a whole bunch of stuff, but a few things I'm going to call out are smart contracts. So say we have smart contract 1, smart contract 2. So this is going to be, let's say this is Ethereum, that's a horrible E. I don't know how to undo this. Let's just scribble that out. And this is an E that looks better. So this is Ethereum 1. Over here, we're going to draw Ethereum 2. And in here, we're going to have S1, S2, but we're going to have S3 now. So you can see that there's a slight difference. So Ethereum 1 is currently a state of maintaining let's say two smart contracts are in their own state. So each smart contract has its own specific state based off of the functions and how they've executed it and all that stuff. And those then make up the Ethereum ecosystem's state for that point in time. But over time, and basically continually over time, the Ethereum ecosystem state continuously manifests and changes and evolves over time. And as it does that, that is a state transition. And you can see that we're transitioning from having 2 smart contracts to 3, because maybe in between that time, somebody's actually submitted and initiated a contract within the ecosystem. So that is an interesting concept, and it's something I learned from here with state transitions. Wanted to share it with you. So that's that piece. next, and actually I got an idea. We could strike these through. As we evolve, we can strike through them together. That's so good. All right, next thing is Turing complete. So I mentioned that subtly, that Ethereum is labeled as a Turing complete kind of ecosystem or machine. And I didn't dive too much into Turing complete because I have a general idea of what it is and I can intuit it. But the one thing I did want to point out that was slightly kind of interesting to me that I saw was the halting problem. So with a machine that is Turing complete, every Turing complete machine runs into this problem called the halting problem. And there's a great video that explains this better than I ever will. Actually, we don't need that. We could just go here. So if you just type in halting problem, the first video that comes up is the one I was thinking about. So in this video, this individual that looks very excited is going to explain what the halting problem is. And I'm not going to explain it here, but the way that Ethereum works around this problem to be Turing complete without having to worry about the baggage that comes with the halting problem is a specific concept called gas, which you may have heard of, I may have heard of, I definitely did hear of prior to this course, but I didn't know necessarily the historical reasoning behind why it exists and why it's so important and critical for the Ethereum ecosystem to function to avoid or mitigate this halting problem. So with the Ethereum virtual machine, EVM, specifically, they're basically throttling the amount of resource that can be sucked out of the ecosystem. So every single smart contract that runs, and you can see that mentioned here, every smart contract basically executes a series of functions and executes a series of computations. And all those computations and functions that are executing, they take up a subset of resources. And the halting problem is basically trying to prevent, or the halting problem is the issue is that these resources could run forever. And if they run forever and they consume all the ecosystem's resources, then the Ethereum ecosystem is kind of useless. You can't use it because it's being taken up by other smart contracts. So the way they're actually working around this and mitigating this is through gas. And this gas is basically metering. It's a metering mechanism. And you can see that mentioned here. And what that's doing is every single smart contract that's executed, it costs a set amount of gas to do so. And by doing that, it's actually throttling the amount of, or throttling in a kind of incentivized way for the developers that create the smart contracts and also the users that use the smart contracts. So if I'm a user and I use a smart contract or a developer that creates one, I want to ensure that the amount of computation and resource that I use is not necessarily exceeding a certain number of gas because it'll become unusable in comparison to my competitors. So it's a really interesting incentive mechanism and a way to kind of manipulate both machines and humans to play nice with this halting problem. So I thought that was really cool. Next thing is elliptic-curve cryptography. So you could tell by me stuttering right before I even get into this that there's no way I'm going to be able to explain this in any way of depth because I am no mathematician. But I have an intuitive understanding of what it means and how it works. This video here is really good at explaining kind of what I don't know if you can hear that. I muted him though. But it explains basically how elliptic curve cryptography works. And this curve here is basically showing you what the elliptic curve is. And if you look at this image here, really the point that I wanted to point out is really highlighted in the sentence here, is that there's two different types of cryptography, if you're not kind of like in the cryptography understanding. There's symmetric, we can say S, and then there's asymmetric, which is A. So asymmetric is what we care about because that's what's happening here. Asymmetric basically has two different keys. There's a private key, and then there's a public key. So the public key is actually derived from the private key inside of this elliptic curve process, or specifically it's a calculation that occurs. And when this is derived, your public key, so we can say this is our public key here, our public key within the Ethereum kind of concept and ethos is it's a derivative or an object that then derives your account that's associated to me. So the account address that you see that you send money to and you receive money from, that's your public key, sort of. And your private key is something that you should never share, and nobody should ever know this. And your private key is kind of like the keys to the kingdom. If anybody gets access to your private keys, then they're getting access to all your money and they can siphon it away. But the point I wanted to point out here that I thought was interesting is that the public key is actually derived in a really interesting way. And I'll read this to you because probably can't verbally explain it better. A public key is a point on an elliptic curve calculated from the private key using elliptic curve multiplication. One cannot calculate the private key from the public key. meaning that nobody should be able to actually derive the private key from the public key. You can't go backwards, but you can go forwards. And I thought the really interesting bit here is actually how the public key is derived from that multiplication concept, where it's basically derived on that curve. And if we go down here in this image, if I make it a little bigger, or I mess everything up, you can see here there's this concept called G. And like I said, I'm not going to be able to explain all this stuff to the best, but G is a concept that is an idea that's associated somewhat to the private key. You can see gradient equals private key. And this gradient is basically going to tangentially find a point on the elliptic curve. And once it finds that tangential point on the curve, then that is going to be your public key. So it's not the first iteration of this, but what's going to happen is this is basically going to do this a trillion times. I don't know a trillion, but a lot. So it's going to have a line here, and a line here, and a line here, and a line here, and a line here. And basically they're going to have a point G, and that tangential point, and actually make it one that makes sense here, say this is G, and then down here is going to be your public key. And you're going to keep doing that over and over and over. And if we actually look at this video, there's a really good explanation, so I highly recommend just watching this video and figuring out what it is. But if not, then let me find this point here. So here you can see basically on the side of this chart, there is a series of points. And all those points are going to be our public, quote unquote, potential public keys. And one of these are chosen at random. And when that's chosen at random, we have no idea basically how that was derived. It's hard to reverse that. So that's kind of, in a nutshell, how that whole concept works. And I thought it was really interesting, so I wanted to share it. So we're going to strike that out now. Moving on. All right, so next in the Ethereum 101 piece was smart contracts. So the point that I wanted to mention around here is I understood the concept of smart contracts prior to coming into this course, but the way that they actually explained it, I thought was probably one of the better ways that I've seen. And specifically, the way that they explained it is an autonomous agent living within kind of like a virtual universe. So you have this, let's say this is our universe, and we have our autonomous agent. This autonomous agent is our smart contract. So within this universe of Ethereum, there's a few different things that can initiate this agent or the smart contract to do things. And you can basically poke them, you can see, you can poke them in two different ways. You can poke them via a message, or you can poke them via a transaction. So there's a graph down here, I'll explain kind of the difference between the two, but really all you need to know is that you can poke the smart contract from two different locations, either from an externally owned account, which is like a human, or you can do it from another smart contract. So you can have an agent here, poke this agent, and then this agent will then do something. And it's a really kind of simplistic way, but it's a really kind of vivid way to understand how smart contracts live within this world. And inside of this world, they can only be poked by a variety of things. And when they're poked by those things, they then execute actions or do things. So it's kind of interesting just to envision all these autonomous agents living within this world, interacting with each other. So I thought that was interesting. I really liked the explanation. So yeah, there you go. All right, next is transactions. So this is pretty quick and straightforward. I just found this graph that I found useful due to the fact that just looking at text and seeing someone talking about what's inside of a transaction is nice, but actually seeing it kind of in like a little block like this kind of gives a good insight to what you would think which is inside of a transaction. And you can see here it's basically stating that a transaction is basically a binary message that's then serialized. And this transaction consists of a series of items. The one point that I kind of called out here that I thought was interesting is the section here for VRS. I didn't really know what that was, so I had to do a bit of Googling. And you can see here basically it's stating that the RNS variables are what actually create a signature because each transaction is signed. So you sign a transaction with your private key so people know that it's from you, and it's also there's no repudiation, so meaning like if I send a transaction I can't be like, no, I didn't send that, because they have proof. It comes right back to you. So those are the two parts for RNS. And then V is for validating the authenticity. So I'm assuming this is just a validation parameter or variable that then validates all the stuff that occurred here with RNS. So I thought that was cool as well. So we're gonna check that off and keep moving. All right, next piece, transactions versus messages. So this is the part I mentioned up here. So I talked about transactions and messages here for the poking of the agents. But what specifically is the difference between the two? So here is a pretty good kind of grid to explain this. I'm going to kind of separate these in 2 instead of 4. So kind of just envision these sections here, mainly due to the fact of the point I'm trying to make. So here you can see we have EOA accounts. So from EOA to EOA, and then from EOA to CA. So like I said, EOA is an externally owned account. So that's like a human. So say H for human. And then a contract, because CA is a smart contract. So what happens here is an EOE does a transaction. And that transaction then could be transaction could encompass a message. So some transactions include messages, some don't. So with this transaction, we can see that an EOE is probably most likely just sending money to another EOA, another human to a human. Here you can see that a human is sending a message to a contract. So that could be them telling the contract to do something, poking them to take an action. So here we can see that we have a CA and then a CA. So we're going from CA to EOA. So this could be the contract then telling a human a message, taking an action, then sending that information to a human. And then here we have a contract speaking to another contract. So this is 2 agents talking to each other in that universe. So this is just going to be a message. And really an important point to point out about this is that whenever you're going from a contract to something else, there is no transaction involved, at least not in this context. So we can see that the contract here is only sending a message. There's no transaction. And here the contract's only sending a message. There's no transaction. So that's kind of one of the discerning points between the two different items there. So the next piece is Merkle Trees. So Merkle Trees are another really convoluted and hard thing to explain. So I'll do my best. All right, so with Merkle Trees, they have a series of Merkle roots, which is like the root of a tree. So they have this kind of going downwards, but another way of thinking about it is going upwards. So you have a tree, and this is probably a really bad tree. It's my horrible drawing. And in this tree, you have the root. And then above that tree, you have branches. So this is, say this is the branch. Branch, branch, branch. And then on those branches, here, you have leaves. Right? Oh, that was a bad leaf. All right, so within the Merkle tree concept, we have our Merkle root. We have, this is going to be an I for intermediate, basically, nodes. And then we have our leaf nodes here. And that same process and concept applies here. So you can see we have our Merkle root here. This Merkle root then has intermediate nodes or branches. And then down at the bottom, we have our leaf nodes, which is our straight up data or transaction. And you can see that this intermediate node here is basically hashing hash 2 and it's hashing hash 3 together. So you hash these 2 hashes together to get this hash. Same thing applies for the Merkle root. You can basically hash all these hashes together then to get the root hash. And then the transactions aren't going to be hashed. These are actually going to be straight up data. So it's going to be either a message or a transaction. So another thing I'll point out here is here you see just one root, Merkle root, but in a real block, because these are blocks, I probably should have pointed that out. These are blocks in the blockchain, and these are a bunch of items inside of the block. There's this concept of different roots. So there's 3 roots. So there's a state root, which is basically a root consisting of all the different state for that specific, that tree of kind of intermediate nodes and leaf nodes. There's also a transaction root, which is basically encompassing all the transaction stuff. And there's a receipts root, which is basically all the receipts that have been exchanged there. So these are the 3 main roots that you'd have within that piece there. So that is that. I hope this is fun and useful for you. And I think this is the last one. So this last piece I wanted to point out is contracts and their immutability. So when you dive into the space and you start thinking more about this and kind of hearing people talk about it, you'll hear them talk about the immutability of the blockchain. This is kind of one of the philosophical points of why people pursue this, this kind of path. And with contracts, one of the biggest selling points for them in the beginning was their immutability, meaning that I would submit a contract to the ecosystem, and that contract actually wouldn't morph or change. Code is law, so when you put the code out there, it can't change. That's the way it is. That's how it's always going to supposedly be. But in the realm of security, that's a big no-no. Reason being is that every contract is going to have exploits, flaws, and bugs. And all of that stuff needs to be changeable. And in the Web 2 world, we're always upgrading things and putting out bug fixes and changing things consistently. And there's always kind of an ethos of change and malleability. So with smart contracts, there actually is a way to upgrade smart contracts over time, which there's a big debate around if this should be the case and if you should be able to upgrade things, but seemingly this is most likely where things are going to go. And the largest pattern that most people use when setting up contracts that can be upgraded is the proxy pattern. And I mentioned here that I want to put a pin in this because I actually do want to make an entire video on this specific topic because I find it fascinating and also find it very important. So there's a great blog post here that I'm going to read, and there's a great video series here that I'm going to watch. And when I do that and consume other resources, I plan on making another video similar to this, explaining it in my own words. So with all that being said, here's a super simple, not probably accurate or specific method of explaining this, but I wanted to show it so you can kind of intuit the image in your head of what this means. So we have a proxy pattern. So what that means, and if you have any experience kind of working in the technical space of Web 2, is you can think of this of either as an API gateway, API, or you can think of it as a load balancer for traffic. So we have this proxy, or even Nginx. So we have this proxy in front of our setup, right? And our users are here, and they're going to interact with this proxy. And say this is our old contract. So we've been using this contract for a couple of months now, but over time we've maybe had some auditors, aka security contract auditors, come in here and look at our code. And they say, hey, there's 7 exploits in here, all of which are simply to exploit, and if they do, all the money is siphoned away. So we, as the developers, need to be like, okay, shit, we need to upgrade this. So what's going to happen is we're actually going to ask our proxy to then look at the new contract that has the upgrades and the features in it. So we're going to then divert all of our traffic and all of our users over to this new contract, either slowly kind of siphoning them off the old one, or doing like a cold cutover and then shifting over here. So that's kind of the concept there. And I hope that was interesting because I find it fascinating. And it is something that we will learn more about in the future. Last but not least, this is my sad little Jaguar. And I wanted to show you this sad Jaguar because I took the quiz. And I got a D-. And with these quizzes, they specifically ask for you to do it within 16 minutes, and there's 32 questions. Reason being is that as a smart contract auditor, apparently you're under pressure all the time because a lot of developers and companies are trying to push their products out, and auditors tend to come in last. So they're kind of in the way between the product going live and it not going live. So you kind of have to rush through all that stuff. And I wanted to put this here to say that I am sad that I got a bad score. But at the same time, I made this video and I'm sharing all this content and I'm learning in public because we're all going to start from somewhere and we're not going to be perfect. So hopefully that you can see my ability to suck at taking this quiz does not correlate to me not wanting to pursue this. So I hope that you found this interesting. I hope that you enjoyed this as much as I did. And Internet, I'll see you in the next video.